I didn't record a new intro or find new background music for part 2 of this unit. Hello, and welcome to AP Physics 1 in a Nutshell, Episode 3, Forces. This is part 2 of Forces in a Nutshell. If you haven't already, go check out part 1. The link will be in the description. Part 1 was an introduction to forces and some of the more common forces that you will see throughout physics. Part 2 will cover 2 of the more complicated forces, as well as the applications of forces. Now on to Part 2. In Part 1, we covered Newton's 3 laws of motion, the basics of weight, normal force, frictional forces, and tension, and we also established that Earth is, indeed, a planet. Before we cover our next 2 forces of the gravitational force and centripetal force, let's talk about net force equations. I briefly mentioned net force equations in part 1, but a net force equation is an application of Newton's second law to solve for a force on an object or the object's acceleration. To use a net force equation, you have to break all of the forces into their x and y components so that all of the forces are perfectly in 2 directions, assuming it is a 2-dimensional problem. You can do this with trig and the angle between the force and the horizontal. When preparing to use a net force equation, you should first draw a free body diagram. A free body diagram is a box with arrows drawn from it representing the forces on an object. This is a good way to visually represent what is happening in the problem, which is very helpful, especially when there are multiple objects with forces in several directions acting on each of them. After that, you should break each force into its components and draw another free body diagram with the components. Some people skip drawing free body diagrams, but I would highly advise against that. It takes about 5 seconds for each one, and it can prevent you from making dumb mistakes. So, do it.
Just do it!
Once you have drawn your free body diagram with just the components, you can set up your net force equation or equations. You will need 1 equation for each object and 1 equation for each direction on each object. For example, 1 equation for all the vertical components on each object, and 1 equation for all of the horizontal components on each object. You set up the equation as the sum of all forces in the direction of the object's motion minus the sum of all forces in the opposite direction of the object's motion, and set that equal to the object's mass times its acceleration. You can set up a system of equations, using equations in different directions and for different objects in the same system, to solve for multiple unknown variables. If the object is not moving in a direction, then the acceleration in that direction is 0, and the forces opposite each other in that direction will be equal. This means that the forces in that direction are balanced. When the forces in all directions on an object are balanced, then that object is in equilibrium, which means that the object is either at rest or is moving at a constant velocity. You will be using net force equations and free body diagrams in just about every unit in physics, so make sure that you are good at this. Now that you know how to use a net force equation, let's move on to the Universal Law of Gravitation and the gravitational force. The Universal Law of Gravitation states that gravity is an attractive force between any 2 objects that have mass. This means that any 2 objects in the universe, no matter how small or how far apart, will experience a force pulling them towards each other as long as both objects have mass. The Universal Law of Gravitation comes with an equation to solve for the gravitational force between any 2 objects. That equation is that the gravitational force is equal to the gravitational constant times the mass of the first object times the mass of the second object, all divided by the distance between the centers of the 2 objects squared. The gravitational constant is equal to 6.67 times 10 to the negative 11th power and is notated by a capital G. Don't get that mixed up with the acceleration of gravity, which is equal to 9.8 and is notated by a lowercase g. If you combine the Universal Law of Gravitation and Newton's second law, you will find that the gravitational constant times the mass of one object over the radius squared is the acceleration of gravity from the other object. If you were to plug in the mass and radius of Earth, you could prove that the acceleration of gravity on Earth is in fact 9.8 meters per second squared. Now let's get on to the last force we will talk about in this unit, the centripetal force. There is a centripetal force on any object when that object is moving in uniform circular motion. That means that the object is rotating at a constant speed. Since the direction is changing, the object's velocity is changing, even though the speed is constant, which means there is an acceleration. Since the speed is not changing, there's not a typical acceleration you would normally use in a net force equation, so you have to do something different. In comes the centripetal force. The centripetal force is not a specific force that you can put on a free body diagram, but you instead change the acceleration in the free body diagram to account for the presence of the centripetal force. When a centripetal force is present, you set the acceleration equal to the speed at which the object is rotating squared, divided by the radius of the circle that the object is rotating in, which is known as the radius of curvature. You can then solve your net force equation like normal, with the centripetal acceleration and all of the other forces acting on the object. Just make sure that you account for whatever force is accelerating the object towards the center of the circle. This will most likely be either tension or static friction. So that concludes AP Physics 1, Forces in a Nutshell Part 2. If you want to see practice problems using the concepts from both forces videos, check out the practice problems video that will be linked in the description. Also, check out the next Physics in a Nutshell video, which will be on work and energy. So good luck with the rest of your physics, and goodbye.